Hi guys, Dr. Colbreth here, and the topic of this video is interference in 2 dimensions. So we're going to continue our discussion of interference, and now we're going to look at 2-dimensional sources. Here we have a source of circular waves, and instead of just considering the propagation along a line, we're going to consider the propagation in 2-dimensional space, and we're going to consider the situation where we have 2 sources of these circular waves. So here is a video that shows these 2 waves, and the 2 waves shown have the same initial phase, meaning they go up together and down together at the same time, and they produce waves which cause an interference out here in space. So to get a better look at this, let's go ahead and take a look at the top view, and here it is in motion. And the 3D animation is nice, but conventionally what we use to represent 2-dimensional waves is a wavefront diagram. So the wavefront diagram would look something like this. And here I have the crests shown in solid lines and the troughs shown in dotted lines. And we have the wavefronts produced by the green source in green and the wavefronts produced by the purple source in purple. And I want to consider a specific point here. So here I've marked a point on the wavefront diagram, and as you can see, we have the crest of a purple wave overlapping with a crest of a green wave. So here is a point of constructive interference, and the reason that this is a point of constructive interference is because if we take a look at the distance that we are from the green wave, we're 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelengths away from the green source, and from the purple source, or 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda away from the source. So there's a path length difference between the green wave and the purple wave arriving at our observer here, but that path length difference is exactly 1 wavelength. And for 2 sources that are in phase, meaning there's no initial phase difference between the sources, they oscillate together, then the path length difference is what determines whether or not we have constructive or destructive interference. And we don't, in the 1D case, if we had a path length difference and an initial phase difference, if we had a phase difference that set up perfect constructive interference, then everywhere along that line we had perfect constructive interference. But in this case, it depends on where we are. Here, we are exactly 1 wavelength further from the purple source than we are from the green source. In other words, we're closer to the green source than we are to the purple source. But if we look here along this line here, right, this is equal distance from both the green source and the purple source. And if we're somewhere in between, we're not going to get constructive interference. We could even have destructive interference. So right here, we have a situation where we have a crest from the purple wave overlapping with a trough from the green wave. So this point here is a point of destructive interference. So in a 2D interference system like this, it depends on where you are, if you're closer to the green wave or if you're closer to the purple wave, and what that path length difference is between the 2 paths, the path from the green source and the path from the purple source. So I want to go back to this point here that's on the star, and I'm going to go ahead and set this wave in motion because the wavefront diagram only shows us 1 point in time. And we got to remember that these sources are emitting waves continuously in time. So as we set this guy in motion and we continue to watch the point here, we see that we have crest, crest, trough, trough, crest, crest, trough, trough. So it's not always crest, crest that gives us constructive interference. It's just the fact that the path length difference creates a phase difference of a full cycle here. And so throughout the entire cycle, the waves are aligned. The crests are aligned and the troughs are aligned. I'm going to go ahead and set that in motion one more time, and we can see then that we have constructive interference all along this line here. Okay? And we also have constructive interference all along this line down here where the path length difference is 0. And so what I'm going to do now is draw those lines on here. These are called the anti-nodal lines, and they show us where the points of constructive interference are due to these 2 sources here. And once again, I'm going to remind you that both of these sources are in phase in this example. Okay, so we have lines of constructive interference. Here the path length difference is 0 lambda. Here the path length difference is 1 lambda, 2 lambda, and then over here 3 lambda. And so these are called the antinodal lines. And we can also draw, well, sometimes I think it's nice to look at these with also the troughs showing, because we can also see that the trough points are also points of constructive interference. And these are called the antinodal lines, and these are the nodal lines, and they show the points of destructive interference. So you can see we have a crest of the green wave overlapping with a trough of the purple wave. This is a place where it really helps to have the in-betweens, the troughs, indicated as well. And when you're working your homework problems, just go ahead and draw dotted lines in between the rings if that'll help you visualize where the troughs are. So we have a crest aligned with a trough, a crest aligned with a trough, and so all of these are going to be points of destructive interference. I just kind of included this animation as a bonus. I thought it was quite beautiful. So this is our two in-phase sources, and I have the anti-nodal lines drawn as well, and you can see these lines of constructive interference propagating out, these waves of constructive interference, and all along these lines the waves totally add, and so we have the antinodal lines. Not a lot to get from this, but it is cool to look at least. So I have been emphatic about the fact that this is for two sources which are in phase, but I want to consider a situation also where we have an initial phase difference between the sources, meaning they do not oscillate in phase together with one another, but they oscillate with some they start at a different part of their cycle. So the example that I'm going to show here, the purple wave is going to be emitting a crest initially, and the green wave is going to be emitting a trough initially. Okay? Otherwise, it's identical to the setup we were looking at earlier. So as these waves propagate, they are still going to create an interference pattern, but we need to consider both the initial phase difference between the two sources and the path length difference between the waves when we calculate the phase difference. And so where we do have crest aligning with crest, we still have a point of constructive interference, but the path length difference is not going to be lambda in this case, because we have a difference in phase due to both the initial phase contribution and the path length difference. So we need to consider the full expression for the phase when we're working problems when there's a path length difference. Let me go ahead and turn off the trough lines for a moment, and we also want to see if we can sort of figure out what the phase difference is between these two waves, and sort of by inspection. And we can see that the purple wave first of all, I want to point out that there's no path length difference between the purple wave and the green wave and the green wave and the purple wave. So if we between the sources, so if we just consider the distance between the sources, this can give us an idea of what the initial phase is. So in this distance here, the purple wave has traveled 1, 2, 3 full wavelengths. Okay, and it ends with a wavefront on the source. Now, if we contrast that with the green wave ends with a trough here on the source. So since we're considering the same distance here traversed by both from the purple point to the green point and from the green point to the purple point, we have it arriving at this other source here at a crest, while the green wave arrives at the purple source with a trough. And so this implies that the initial phase difference between the two waves is pi, right? We are emitting a trough first from this wave, and we are emitting a crest first from this source here. And since these are exactly out of phase, that is a phase difference of pi. So this is very similar to one-dimensional. The equations do not change much from the one-dimensional to the two-dimensional case. It just requires a little bit of more thinking and considering things. Really, all we've changed is our path length difference from a delta x to a delta r, meaning we need to calculate the actual point-to-point distance between the source and the point of interest in order to calculate the difference in the path length. And so once again, we're going to get perfectly constructive interference when the contribution from the path length and the contribution from the initial phase are some multiple of 2 pi. And similarly, we're going to get perfectly destructive interference when the path length contribution and the initial phase contribution are some odd multiple of pi. So I have two example problems. I have a conceptual example problem and a quantitative example problem. So go ahead and take a look at both of those videos, and I hope they are helpful for you. Thanks a lot.